In this video for VCE Algorithmics students, we learn how to analyze code for time complexity by direct inspection. Typically, we'll expect to see some nested loops and some different time complexities combined and added together. Now, this first example uses one variable. In the first nested loop, for each item in X, we consider every item in X again. So suppose we have three items. First, we set I to alpha and j to alpha, and we run a constant time operation printing alpha alpha. And then look at how we loop through. For each item in the first list, or for each item in the outer loop, which is in the main list, we loop through every item in the list again. So we go alpha alpha, alpha bravo, alpha Charlie. Then we take Bravo and we go Bravo Alpha, Bravo Bravo, Bravo Charlie, and so on. And we do that over and over again until we get down to Charlie Charlie. Now, hopefully it's fairly clear that this is going to run x squared times because we're performing x squared constant operations. We generally ignore the constants because remember, for big O time complexity, we're considering how the time complexity grows as the input size or as the problem size grows. So this is the first thing you need to get your head around, is just looking for a nested list and pretty much multiplying the things together most of the time, but not all the time. Consider this next example where we have two lists of elements, x and y. I stuck an extra constant time operation in there, that printing out that line, just to make the point that it doesn't do anything. So what is going to be our big O notation for this list? Pause video if you're not sure, have a little think, and hopefully you can see why it's going to be big O of xy, because we are growing with x times y. Now, notice it's not going to be n squared. One of the mistakes people make in algo exams is they just want to write everything in terms of n squared, either when there's n and some other variables, or there's a whole bunch of other variables. So we need to maintain the initial variables that we're given, because, I mean, here n is meaningless. We don't know that it's strictly quadratic because we don't know how x and y are increasing. Right. Next, we're going to consider how to combine multiple things added together. So we've dealt with some nested loops where one thing is done inside another thing. Now let's look at what happens when we do one thing followed by another thing. What do you think is the time complexity of each of these two loops? Now, I think the first one is hopefully fairly obvious. It's going to be x squared because for the same reason of the first one. And for the second one, notice that we stop at x minus 1 or x minus 3. We don't really care about those constant changes. I mean, x minus 1 is so close to x when x gets very, very large. What we could read that pretty much as 1 to x for all three lines on that second loop. And so we would treat that as big O of x cubed. Now, when we add these together, remember that we're trying to find an upper bound such that if I multiply the big O thingy by a constant, it will always be bigger than the number of operations being performed for sufficiently large numbers of n. I've used n, but obviously multiple variables, it would be those variables. So we're looking for an upper bound. What we're doing here, and this is terrible notation, by the way, but just go with it. We are adding x squared operations with x cubed operations. Well, we know that x cubed is bigger than x squared, so we could really treat this for an upper bound. We could call it x cubed plus x cubed, and that would be 2x cubed. And since we don't really care about constants, we would just call that big O of x cubed. So we have to be on the lookout for when one term dominates another term. When we can be absolutely certain that one term is bigger than another term, we can ignore the smaller term. Okay, but don't oversimplify things. Consider this next example. I think the first part, analyzing each loop, should be obvious. This is xy, this is xyz. Now, in this case, we can see that we're going to have xy plus xyz. Can we be sure that one of these things is going to dominate that? For example, is xyz always going to be bigger than xy? Well, yeah, it is. We're assuming all positive numbers because these refer to problem sizes. So we could refer to this as big O of x, y, z. No problem. You can tell from the way these videos go, the next one is going to be a problem. So let's be a little bit more switched on. Write down the time complexity for each of these two loops. And you should have x for the first one and yz for the second one. Now, when we add these together, x plus yz, we might expect that if everything was roughly similar, then yz is going to be bigger than x. But we don't know that. X could be increasing far more rapidly. And so we have to write this as big O of x plus yz. Because one of those things is going to get larger than the other things, necessarily, unless they're exactly the same, in which case that's still fine. And so doing a constant times x plus yz is always going to be greater than the number of operations being performed, because whichever one of those two terms dominates, be it the x or the yz, that's going to be included, and that is going to give us that upper boundary. Okay, next we're going to consider a graphing algorithm. Now let's consider the first loop. We've got for each vertex, we're looking at each edge attached to the vertex. And you might be tempted to say, well, this is v times e. However, it's not quite that simple because each edge is not attached to every single vertex. Okay? Each edge is only going to be counted twice as we go along. So it's actually going to be big O of v plus e, because every edge is going to be counted only twice, independent of the number of vertices. Obviously, we expect them to be somewhat related, but we could deal with a very dense or very sparse graph. So we wouldn't want to assume that edges is going to go up with vertices. The only situation that we might do that is if we were considering a complete graph, in which case we'd say that E is approaching v plus 1 over 2, meaning that the handshake lemma, which would give us v plus essentially v squared, which would give us v squared. But we haven't been told that here, so we're going to go with v plus E. For the next one, I think that one is a little bit less controversial. We can see every vertex, we are considering every other vertex, and then we're doing some stuff. Whether the edge exists or not doesn't make any difference to what we do. Well, if it does, we do one thing. If it doesn't, we do the other thing. So the edges that exist don't do anything here. Now let's consider how we combine these. We've got v plus e plus v squared, and we know that e and v are somewhat independent. We can't say that one is always going to be bigger or smaller than the other. However, we do know that v squared is always going to be bigger than v. So we can drop that v squared term, sorry, we can drop the v term and end up with just e plus v squared. Okay, the final one to consider is when we call one function inside another function. This came up in an algo exam 24, 25, something like that. They're quite big on you annotating the code as we go along. So the way I've been showing you on this PowerPoint is not that far away from what you would be expected to do. We are going to analyze the time complexity of main. Okay, and so straight away, hopefully you can see that our time complexity shouldn't have an x in it, because helper takes in x, but that's really just a placeholder for whatever helper is given. So the inputs we're putting into main should be y and z. Now the first loop is, you've got to think quite carefully about it. The for loop, we are running y times, and for each of those y times, we are doing helper, which is y squared. So we're actually going to have big O of y cubed. Now you might think it's going to be quadratic, so consider a couple of counterexamples. If we just called helper of y without that for loop, that would definitely be quadratic, because we can see the helper runs in quadratic time, but we are doing it a bunch of times. So we're going to run y squared, y times, which gives us y cubed. If you got that wrong, perhaps pause and revise your answer for the next one. So we can see for the next loop, we are running the two for loops, a total of y times z times, as in y multiplied by z runs. And each of those we're running helper on yz, which is going to give us yz squared. So we're going to end up with yz squared for the helper function run yz times, which gives us yz all cubed or y cubed z cubed. Now we're running these one after the other, so we're going to add them together, and then we consider, can we eliminate any of these? And yeah, we can. We can see that for sufficiently large numbers of z, y cubed z cubed is going to be bigger than y cubed, and so this is going to simplify to y cubed z cubed. Okay, hopefully that has been helpful. Questions in the comments.